right, this is section 3 in chapter 4. We're going to talk about relative motion. And this can get a little confusing. You do need to just make sure that you're paying attention to what's going on. And this is going to be one of those instances where, too, it's going to be extremely helpful to draw a sketch. In all of these vector problems, you're going to have to sketch the problem out in order to really understand what's going on and be able to do the math. So relative motion means the motion of one object relative to another. So we talked about frame of reference, and most of the time our frame of reference is the Earth or is the x-axis or something like that. But now we're going to look at two objects. They're both moving, and how's their motion, their relative motion is the motion of one object relative to the other. So we look at a couple examples. You observe a railroad worker walking in the forward direction at 1.2 meters per second relative to the train, moving at 15 meters per second relative to you. So you are standing still. The train is moving and the worker is moving. So it appears that the worker is moving at 16.2 meters per second because since they're both going in exactly the same direction, it's really easy. You simply add the two magnitudes together. And of course, the direction will be the same direction as the train. Okay, so that's super easy. All right, let's look at another one. Right there. All right, so what happens if the worker is going in the opposite direction of the train and you're still standing there watching all this going on? So now the worker is going in the opposite direction but with the same speed. Okay, so this time, again, we're going to add the two vectors together, but because they're going in opposite directions, we have a negative sign, and so we're adding sign numbers, which means that I'm actually going to subtract the two magnitudes, and the speed would be 13.8 meters per second relative to what I'm seeing as I'm watching this go on. Okay, and so those are pretty easy examples because we're talking about motion just in one direction. And it's all on that horizontal plane. It gets a little trickier when we start throwing in angles. So if the velocity of the train with respect to the ground is represented by VGT, and this is where you got to pay attention because all of these subscripts mean something. So each one of them should be a little bit different. So the velocity of a train with respect to ground, we're going to call that TG. The vector of the worker with respect to the train, the one that's on the train, would be WT, and the person that's on the ground watching would be WG. So we can find the velocity of the worker relative to the ground by simply adding the velocity of the worker relative to the train and the train relative to the ground. We're going to add those two vectors together. So here's some examples, the two examples that we talked about. So as long as they're going in the same direction, here's the worker on the train, here's the train on the ground. So the worker on the ground is seeing them both going in the same direction, so you're simply going to add them together. In the other instance where the worker was going on the train was going the opposite direction, so again, still going in the opposite direction, the train to the ground is going in that direction. So the velocity of the velocity of the worker relative to the ground is going to look like that. So we use the subscripts to just kind of help us keep track of what's going on where. Okay. So again, if they're going in the same direction, we're simply going to add them together. If two motions don't occur along a straight line, then we still use the same approach. The same approach is used when is applied to the worker on the train. That's still true. But the velocity of the one object relative to the other is found by adding the velocity vectors together. Okay, so let's get an example. So now, instead of just walking back and forth horizontally, we're going to look at climbing up the train while the train is moving horizontally. So in this figure, you're climbing up, so that's worker on the train, he's climbing up, and then train to the ground is going this way. So we're just going to put our vectors head to tail and find the resultant. The person on the ground is going to be the resultant, worker to ground. Okay. All right. So, and this is the same thing. So we have a vector 1, 2 would be the first object relative to the second object. And then you're going to have another velocity vector or vector of the second object relative to the third object. So to find the resultant, that would be the vector of the first object relative to the third object, since that's going to be the resultant of those two vectors added together. Okay. So here's our three objects, 1, 2, and 3. So again, velocity or vector 1 to 2 and 2 to 3, when we add them together, that gives us the vector for 1 to 3. After you get all that kind of labeled and straightened out, it's the same concepts for adding those vectors together that we've used before. Nothing else has changed. We just have lots and lots of subscripts to keep track of. All right, so worker in figure 419 climbs a ladder with a speed of VWT, that's worker on the train, of 0.2 meters per second. As the train coasts forward at a speed, that's train to the ground, of 0.7 meters per second, find the speed and direction of the worker relative to the ground. Okay, so we've got to find the X and Y components of the worker on the train. So since he is climbing straight up the ladder, he does not have an X component, only a Y component. And because the train is not going vertically off the track, it does not have a Y component, it only has an X component. So so we're going to do the same thing we did before. We're going to add the two X components together, then we're going to add the two Y components together, and that will give us the components of our resultant VWG, worker to ground. So WX, that's going to be 0 plus 0.7. And then worker to ground Y is going to be 0.2 plus 0. Then we're going to square those numbers, take the square root, and that gives us 0.73. And we're going to find the angle, we're going to do inverse tangent of the Y component over the X component, and that's going to give us 16 degrees. So once you get all of the components labeled correctly and figure out what's going where, we just use those same methods for adding and subtracting vectors that we had in the last section. Okay. So here is another example. You're riding in a boat whose speed is relative to the water is 6.1 meters per second. The boat points at an angle of 25 degrees upstream on the river flowing at 1.4 meters per second. What is your speed relative to the ground? What is your direction and travel relative to the ground? Give your answers in degrees upstream. So we're going to choose the x-axis to be perpendicular to the river. So x is going across, straight across, y is going straight up and down. And the y-axis is pointing upstream. With these choices, the velocity of the boat relative to the water is 25 degrees above the x-axis, so that's right there. In addition, the velocity of the water relative to the ground has a magnitude of 1.4. So that's going to be this one right here because it's flowing downstream, so that's why that vector is going in that direction. Boat to the water is 6.1, that's 1.4, and this is 25 degrees. No, it's 25 degrees to the x with the x-axis. Sorry, let me erase that. Okay, so we're first going to find the velocity of the boat. So we're going to use 1, 3. I don't know why they used letter. Okay, they're just using the 1 and the 3 and all that. So we're going to replace those numbers with letters. So the velocity of the boat to the ground is going to be equal to the velocity of the boat with the water and the water with the ground. And that's this resultant vector right here. So that is going to be Pythagorean theorem. Using Pythagorean theorem to find the magnitude of that, that's going to be the x component squared plus the y component squared, and then of course we're going to use this inverse tangent to find the angle of that. We know VBW is 6.1 meters per second, WG is 1.4, and we're looking for that resultant. Okay. All right. And the angle. So let's look at the next page to finish this off. Oops. All right. So to find the x component of the boat with the water, we're going to take 6.1 times the cosine of 25. And because it's going at an angle, it's not vertical, it's not horizontal, it has two components. So we're going to have an x component, and then we're going to find the y component by saying 6.1 times the sine of 25. That gives us those two amounts. The velocity of the water to the ground, the x component is 0. It's not flowing horizontally, it's flowing down. And the velocity x going downstream, so that's negative 1.4 meters per second squared. So then all we're going to do is add our two x's together, which is 5.5 plus 0. We're going to add our two y's together, which is 2.6 plus negative 1.4. And then we're going to plug those into Pythagorean theorem and solve for the velocity of the boat to the ground. To find the angle, we're going to do second inverse tangent of the y component over the x component, which gives us 12 degrees. We know it's going upstream because this is a positive number. Okay. Oops. Okay, and that is going to end for section 4.3.